In this video, I'll give you some tips for solving the ALEKS problem called Recognizing Typical LCAO Molecular Orbitals. This problem is going to give us a picture of a molecular orbital, and we have 3 questions to answer about that orbital. I think it's easiest if we start with the second question, which asks if it's a bonding or anti-bonding MO. And so for this particular ALEKS problem, there are only 2 types of orbitals, there are only 2 types of bonds that ALEKS represents, and those are sigma bonds or pi bonds. If you have a sigma bonding orbital, a sigma bond in a bonding orbital, what you're going to see are the 2 nuclei, which are represented by dots like that, and then you are going to see electron density. I think I'm just going to use like a highlighter. You're going to see electron density in between those 2 dots. This is represented by just like this light pink color. So it's going to be something that doesn't always look exactly like this, but what you're going to see are the dots, and then there's definitely this shaded area in the middle, which is exactly what I'm looking at over here. Now, of course, my picture doesn't look exactly like this one, and yours may not as well. Sometimes they get kind of funny. Sometimes they have like additional electron density on the outside like that. Sometimes they are larger, like mine, larger than what's represented. But the key is between those 2 nuclei, you definitely have electron density represented by this pink stuff. And so since that's what I have, I do have electron density in between my 2 orbitals, or excuse me, in between my 2 nuclei. That means that I definitely have a bonding orbital. Now, if you have a pi bond, and the way that you're going to recognize that you have a pi bond in a bonding orbital is just by the way that it looks. You're going to have your 2 nuclei. There is not going to be electron density in between those 2 nuclei, but you are going to see electron density above the nuclei and below the nuclei. So these are what your bonding orbitals are going to look like, or something that kind of resembles that. Sigma bond, pi bond. Now, your anti-bonding orbitals are, for your sigma bond, your anti-bonding orbitals are going to have electron density that is not in between the 2 nuclei. So it's going to look something like this. And again, it may not look exactly like this, but the key here is that you are not going to have any electron density in between those 2 nuclei. And you're not going to have something that looks like a pi bond. So the pi bond, our electron density is delocalized or spread out over the general region of space for both of those nuclei. With a sigma antibonding orbital, our electron density is not distributed across the area of both nuclei. It's just kind of hanging out on one side. So this is an antibonding. An antibonding pi orbital is kind of difficult to draw. We're going to have our 2 nuclei, and then basically what you're going to see are just something that kind of looks like this. So again, there's going to be no electron density in between the 2 nuclei, and there's also going to be no merging of the electron density above or below the nuclei. So it's going to look like that. All right, so I've got a bonding sigma orbital. I think the next easiest question to answer is to write the symbol for this molecular orbital. So to do that, you're going to have to decide if it's a sigma bond or a pi bond, and you're going to do that by just kind of looking at these different pictures and matching them up with yours as close as possible. Mine looks most like a sigma bond, even though I don't have these little guys out here. I do have this pattern right there. And so once you decide whether it's sigma or pi, you're going to use these symbols over here. You're going to write whether it's a sigma bond or a pi bond. And then in subscript down here, you're going to write the name of the actual orbitals that are used in this particular bond. ALEKS actually gives you that. So if you read over in the problem, it'll tell you what the name is of the atomic orbitals. For me, it is 3s. And that is going to go down in a subscript. Remember, that's a lowercase s, or if it's p, it's a lowercase p. If this were an anti-bonding orbital, then you need to use the asterisk symbol as a superscript. That is what's used to indicate that it is anti-bonding. All right, so add this for an anti-bonding orbital. And then last but not least, we're going to answer a question about the relative energy, comparing the energy of the molecular orbital to the energy of the original atomic orbitals, which for me is 3s. There's a pretty standard pattern here. If it's a bonding orbital, then the molecular orbital is lower in energy, and that's just a rule. If it's an anti-bonding orbital, then the molecular orbital is higher in energy. There's no situation in which the orbitals are the same or there's not enough information to decide, so those are never going to be answers. Hopefully this makes this problem a little bit easier for you.